Okay, now let's talk a little bit about a population regression line. And that sounds kind of weird, but I want to remind you that the regression line that we found is called a y hat, and it's a plus bx. So what we have to do is we have to understand that we have a sample of x and y, and that's only going to give us an approximation of the regression line. So what I want you guys to think about is that we have the mean of the y hats. So if I got a different x and y, I would get a different regression line. So if I went out and took another sample, just like everything else, our sample is going to be a little bit off. So our population regression line actually kind of looks like this. It's the mean of the y hat. So I did mu of y hat equals alpha plus beta x. So for each x, it has a mean. So around that mean, I don't like that word sample right there. So around that mean, we have a little normal distribution. Okay? We have every single x has its very own little normal distribution that hangs around it. If I had another one in the middle, I would have another normal distribution. So every single one has a normal distribution. And what falls on this normal distribution are our errors. So our errors should fall anywhere around in here with a normal distribution. So our errors should be like here or here, and if they're way out here, this error probably is an outlier, right? It was very unlikely to happen because if we get really far from the mean, this becomes less likely to happen. That's one of the ways that we can identify outliers. But one of the things we want to make sure is that this is normally distributed so that each one of these errors from the mean are normal. So one of the ways we do that is to study the residuals. Residuals are basically our errors. So that is the difference between the actual measured value. This is the one we got. This is y. This right here is y hat at the same x. So this one is at 2.9. So what we would do, and this is at, I'll just say I, because it's number 1, 2, 3. So this is y hat 3, and this is y number 3. So E number 3 would be y number 3 minus y hat number 3. And what is that? What does that look like? This looks like it's about, I gotta erase these now. I don't know. What's the middle between there? That's 0.4, 0.3. So that's about 6. So I would say this is 6.0. The line at 2.9 is, let's see, that would be 4.7 maybe. So our residual on this particular one looks to be about 1.3 would be our residual. Now, we don't really know if that's weird unless we would have to standardize it in order to find out whether that was outside of 3 standard deviations away from the mean. I don't really know. So that is something we would have to do. So we actually do that. Sometimes we do standardized residuals. And there's a lot of different things that we do with the residuals to actually see if there's any that are kind of out of the ordinary. So what we're actually going to do is these residuals should be a normal distribution. So if I take all the residuals for this, for each one of these data points, they should be normally distributed. They should have an average of 0, and they should have the same standard deviation. So my bell curves for each one of these should be exactly the same size, is what I'm saying. So if my bell curves for each of these isn't exactly the same size, then something's not right. then maybe I have non-constant variance and I have a little bit of a problem. So each one of these bell curves should be about the 3 and the 3 should be about in the same distance from the mean or from the line. Okay. So what we're going to do is we're going to plot the residuals against the x values. So here I have my x values on the x-axis, just like usual, but I'm going to do my residuals instead. So I want you to see what they look like. So this one, the residuals as x, when x was really a small number, the residuals were close to 0. But as x got larger, my residuals are bigger. So that would tell me that what's happening is my normal distribution here is really tiny, but my normal distribution here is really big. But wait a minute, they're supposed to be the same size. So that's not okay. The variation is not constant. This is bad. So, or we can say standard deviation too. Standard deviation is not constant. Same thing. Variation, variance, variability, all of these things are the same thing, and I don't know which one that I'll put on the test. So this one is bad also, because what's happening here is that when x is small, my residuals are consistently above 0, and then when it's in the middle, it's below 0, but then when it gets big again, it's above 0. So what that tells me is that I probably have something like this shape between x and y. So this tells me that x and y are not linearly related. So I get a smile. Sometimes you'll see it as a rainbow, something like that. That tells me that x and y are not linear. They have something else going on. Now we look at this one. What do you see? I hope you say nothing, because that's what you should see. See nothing. Seeing nothing is good in residual plots. So we're going to put, here's my x and here's my residuals. Nothing there. Okay, so that's a really, really important factor that we have to do, that I will be testing you on. So how do we make this plot? So what we're going to do is, let's say, and I just did, so I know I have it. So we've already done our, so this is after we've run our ln-reg t-test. So you have to run ln-reg t-test first. And then after L1 and L2 are our x and y. So that's what I'm assuming right now. Of course, your lists may be different. So there's the ln-reg t-test that I just did, or, well, last time, which, okay, I'm doing these back to back. So yeah, I just did it. Okay, so this is the one for the Alex score versus the first test score. So I'm going to go over here, go to stat plot. And actually, before I go to stat plot, I want to do just kind of a note here. If you still have your regression line in Y1 and turn, then clear it. We'll just clear it, okay? So you do that by hitting Y equals, no second, just hit Y equals, and clear. Okay, that's going to make your life easy. Then you don't have to worry about it. So go second, Y equals. I'm going to go back to my stat plot. Okay, I'm going to do a scatter plot. So the first type is the same. Then X1 should say, X-list should still say L1. Now L2 should be wherever this should be, my Y list needs to be my residuals. So hit list. So second stat brings up list. And you'll see the list of names. Sometimes you have to scroll down a little farther, but you see number 7 right here. Some of you may have other lists that you have to get to, but number 7 is my residuals. And then I guess mark, you can do what you want. And then I hit zoom 9. There's my residuals. Now, lots of things that I could argue about this particular one. Now, again, all that I would expect you to do is just take the picture of it and just draw it from the best you can from your calculator. If you really want to be fancy and plug your calculator in, then that's fine with me. Okay. I've had people take pictures of it too. So now I see these extra ones out here that look like they're kind of close. So I don't know. I mean, you could kind of, if you really wanted to get strict, but there's really only one data point out here. So I really don't see an overall coning effect. And like I said, don't be too strict about it. So I'm seeing that I don't see any smiles or rainbows. I don't see any cones. No, I don't. I really don't see anything going on but a blob. And that's what I'm looking for. So this is good. Okay. No violations. So now let's talk about the next thing. Normal probability plots. Now a normal probability plot is going to tell you whether your residuals are normally distributed. Now when we look at a normal probability plot, they're plotting your actual numbers, your residuals, against where they should be, okay? The probability that they're in that particular spot, okay? And then this is a cumulative probability, by the way. And so what happens is you can kind of see this shape. This one is good. Actually, this one is great. They're more or less in a straight line. I mean, they're a little bit off, but they're more or less in a straight line. If it looks like an S, your residuals are skewed. Now look at this one. This one goes way off the line. This one does all kinds of weird things. Okay, this is telling you that you have skewed data. This one, definitely an S. Again, skewed. Okay, this one is skewed. This one is skewed. So all these other ones are bad. They're going off of normal because normal should go in a straight line. So that's what we're looking for. Looking for a straight line. That's your normal probability plot. So let's look at our normal probability plot for our data that we have. So again, I have my residual versus my X values. So what I'm going to do is I'm going to change this. So I'm going to go second Y equals. I'm just going to go to this first plot. I'm just going to change the first plot. I'm not going to try to turn another one on. So type is normal probability plot. Now we go to type, it's the very last one you see. So I got a side arrow, remember. It has to be the side arrow. Use the side arrow. Because remember, you can't go down to it. You have to use the side arrow. Hit enter to call it. Now my data list is going to be the residuals. So again, I'm going to hit second stat and bring up number 7 residuals. Data axis, X is fine. That just keeps it this direction. And that keeps it side to side instead of up and down, which is what we want. Mark, I do not care. Okay. Zoom 9. Okay, and there's what we have. Oops. I don't need that. All right, so let's look at this and let's compare this to the one we did. And it says, hint, don't be too strict. This goofy thing. All right, so looking at it's funny because it looks very different on the calculator versus the program that I used. It almost tends to go off here, but what I like to do is draw this line. And look at that. That doesn't really go off the line too much. This does a little bit. It tends to go down just a tiny, tiny bit down here, but I'm not overly concerned with that it's doing that. So if I look at this, maybe just a little bit kind of goes off my line, but it doesn't very much. And it might be slightly, my residuals might be slightly skewed. Another way to tell sometimes, I'll just do this real quick, is what I like to do too, is you can actually do a histogram of your residuals just to see. And you could do stat plot and go to type and just go to the histogram one and keep residuals on there. Zoom 9. They don't look very skewed. That's the terrible. I hate the number of bins that has. I would want more. But if I look at that, don't be too strict about it. It's pretty close to normally distributed. As far as only having 20 data points, it's really hard to get 20 data points to be normally distributed. Or 15, right? We only have 15, so. All right. So again, this one would be, I would consider this okay. It's not coming out for some reason. I would consider this one to be okay. Assumption of normality is not violated. All right, so one more subject and then I can leave you alone, and then I only have one more video to make. So we've been using this linreg t-test to find regression line in R squared, but one of the ways we can actually do a test, we can actually do a test to see if our slope is significantly different from 0. Now remember, a 0 slope would just be this. That would just be, well, wherever y bar is, that's where the thing would be. So we want to make sure that our slope is significantly different from 0, because if the slope isn't significantly different from 0, then x and y really have no linear connection, no linear correlation, and you might as well, like I said, use one var stats and just analyze y. Who cares? Don't really need the x's anymore. So why do you need more data? So the null and alternative hypothesis looks like this, and this is the Greek letter beta. So h naught is beta equals 0. The alternative is beta is not equal to 0. Yes, you can actually do one-tailed test for these. We're not going to do that in here. We're going to just restrict our analysis to a two-tailed test for the slope of the line to say whether it is significant or not. So now we're going to use our t and p value in the output to determine whether this is right. So let's look at this test that we just did. Let's go over here. This darn thing. Okay. So go back to stat, test, linreg t-test, and calculate. And now you'll notice that the first thing it does is y equals a plus bx. We've seen this. The beta not equal to 0 and rho not equal to 0. Don't worry about rho. We're not going to do that in this class. Beta not equal to 0. It's just the equivalent tests. Your test statistic, t, is 2.612, and our p-value is 0.0215. So at the 5% significance level, we would reject the h naught, and have enough evidence to conclude that the population slope is not 0, and therefore the regression is useful in predicting test scores. So if we reject, then we have a useful regression because this is significantly different from 0. So we have something. So on the other hand, at the 1% significance level, we could not reject the null, and we would not have enough evidence to say the slope was significant from 0. So at the 1% significance level, we couldn't say that this was a useful regression. So it depends on how sure we want to be. You guys have done hypothesis tests enough to know that it all comes down to that significance level and how much of a chance of a type 1 error we're willing to accept. All right, so that's it. And that wasn't too painful, right? One more video to watch after this, and then you guys will be done.